So now we're looking at lesson 2 in our thermochemistry unit. This is dealing with enthalpy and then a couple different heats, heat of fusion, vaporization, and combustion. We'll talk about the difference between those in a minute here. First things first, though, we need to know what enthalpy is. So if you look at the definition for enthalpy, it's the heat change associated with a chemical process in general. Okay. Now, as we do these problems, you're going to see this delta H a lot. Delta H is actually the symbol for enthalpy. Okay. Now, if delta H is negative, it's telling you that the energy is going to be released from the systems to surroundings, okay? And if you think about the definition of energy released from system to surroundings, that is an exothermic process, okay, like we talked about in the last lesson. If delta H is a positive number, energy is absorbed from the systems to the surroundings, and this is an endothermic process. So if you look here, this reaction, so calcium oxide is reacted with water, forms calcium hydroxide. You are told that the enthalpy here, delta H, is negative 65.2 kilojoules, which will tell you it's an exothermic process. This reaction here, sodium bicarbonate and energy, or a certain amount, gives you sodium carbonate and water, so it basically decomposes, and carbon dioxide. You look here, delta H value is 129 kilojoules, which is a positive number, which means it's an endothermic process. Okay, so using this enthalpy, we'll use it in a couple different ways. So heat of vaporization, or enthalpy of vaporization, you'll see here that delta H. Okay, so you can say it either way, heat of vaporization or enthalpy of vaporization, doesn't really matter. So looking at this, it is going to be the heat required to evaporate a substance at its boiling point. So what's going to be important here is you have something undergoing the boiling point. So you're always looking at the liquid and gas phase change. It could be liquid to gas or gas to liquid. Okay. So again, that's mentioned here, liquid gas phase change. Your equation is going to be Q, which is heat, like we've been talking about, is this delta H value, the V to show you it's vaporization, times the mass divided by the molar mass. Okay. Only going to make sense when we give it a try here. So we've got 49.5 grams of water is boiled at its boiling point, 100 degrees Celsius. Again, you're going to know that you're using the heat of vaporization equation because you do have that boiling point in here. Your delta HV value is given to you. That's specific for water. And you want to know how many kilojoules are required, which means that you need to solve for your Q value. Okay, so using your equation, Q equals delta HV times the mass divided by the molar mass. We're solving for Q, so we're going to plug in the delta HV, which comes from here. So we've got 40.7 times the mass, which is 49.5, divided by the molar mass. Keep in mind we have water here, H2O. You add up the molar mass using the periodic table. 2 times 1 for hydrogen plus 16 for oxygen is a total of 18. And you go ahead and calculate. So 40.7 times 49.5 divided by 18, you're looking at about 112 kilojoules of energy. And that's it. So if you understand how to do that problem, heat of vaporization, heat of fusion is going to be very similar. So heat of fusion, which is delta HF, show you fusion, the heat required to melt a substance, or freeze a substance at its melting point. Okay, so looking here, again, used for problems dealing with a solid-liquid phase change this time. Doesn't matter if it's melting or freezing. So this is the equation we have. It looks very similar to the equation above. The only difference is you're going to use the delta HF value that's given to you in the problem. So looking at this, we've got 31.5 grams of water melted at a melting point of 0 degrees Celsius. That melting point is going to clue you when you're using the delta HF or heat of fusion equation. And that would also tell you that right here in this number that you're given. You're trying to figure out how many kilojoules are required. So once again, you are solving for Q. So Q equals delta HF, which is this number right here, 6.02, times the mass given to you in the problem here, 6.5, divided by the molar mass. Once again, notice we do have water, same molar mass at 18. So if you take 6.02 times 31.5 divided by 18, you're looking at 10.54 kilojoules. That's it for these problems. Now, the third type, heat of combustion, is a little different. Okay, so we're going to be looking at this problem with a little bit of different lens. We are going to be dealing with reactions here. We are going to be thinking about the coefficients that we have for these problems. Give myself a little bit of room for this problem here. Okay, so looking at the last type here, which is our heat of combustion. So first of all, we need to know what that means. So delta HC is how it's abbreviated. It's the heat released when a substance undergoes a combustion reaction. Okay, so looking here, the equation delta HC is going to be the sum of the delta H of the products minus the sum of the delta H of reactants. Okay, so what you're going to need for this is you're going to need a reaction. It may or may not be balanced. This one already is for you. You know that some coefficients already. And you are going to need some sort of table that gives you the information for these different compounds. You will not be expected to know these on your own. So we've got the 4 compounds we have: CH4, which is methane, O2, which is oxygen, CO2, and water. So what we need to do is we need to add up the sum of the delta H of the products and then subtract the sum of the delta H of the reactants. Okay, so make sure you know which are the products, which are the reactants. These, of course, pen back here. These, of course, the products. These are the reactants. Okay, so our products, notice we have 1 CO2 and 2 waters. That's going to matter. So our products, we'll start them first. So we've got 1 times the number for CO2, which comes here, negative 393.5. You add to that 2, because there's a 2 here, times the number for water. Okay, and then you need to subtract, using this equation, the sum of the reactants. Okay, now you need to watch your sign here because you do have a negative here. So subtract. We'll start with the reactants now. We've got 1 methane, so 1 times this number. So negative 74.87 times 1, only one of them, plus we've got 2 oxygens. The number for oxygen is 0, so 2 times 0. I like to put these in parentheses when I put them in my calculator. Okay, so if you put 1 times negative 393.5 plus 2 times negative 285.8 in your calculator, parentheses, minus, parentheses, negative 74.87 times 1 plus 2 times 0. Again, this basically equals 0, so it doesn't really matter. You should get a value of negative 890 if I round. And then your units will match the units that are in this table, so kilojoules. And that's it for these problems. So you're going to try out in your practice bag of lesson 2, see if you can handle these types of heat of fusion, combustion, and vaporization problems.